Okay, welcome everyone to the combinatorics section of the ICM. And welcome to our speaker, Federico Ardila from San Francisco State University. Federico has uploaded his lecture, so we'll see a film of it now. And the lecture is about the geometry of geometries, Matroid theory, old and new. So we'll now see the recorded lecture.
Thank you so much to the organizers for the opportunity to speak here today. It is a great honor, and it's very exciting to get to share a little bit of mathematics that I love. So my talk today will be called The Geometry of Geometries, Matroid Theory, Old and New. I'm going to be talking about the work of a lot of people, and this includes my co-authors, students, and teachers. I want to thank you because it's really been a great joy to learn from you all, to work with you all. And I think you all helped me understand that mathematics is something that we do in community, and I've really had a lot of fun going on mathematical adventures with you all and learning from you all. The summary of my talk is the following. I'm hoping to convince you that matroids are geometric. So first I need to tell you what matroids are, and then I will explain to you why I really think that they're very geometric objects that should be understood that way. And the second thing that I would like to talk about is just how this fact that matroids are geometric is really very helpful for geometry and also for combinatorics. Okay. So to begin, let me just give a brief introduction to matroids. So the idea of matroids is that they are combinatorial objects that are supposed to capture the combinatorial essence of independence. There are many notions of independence in mathematics, and matroids get at what these notions have in common. The motivating example, which is what gave birth to the theory, is coming from linear algebra. So it goes like this. So you start with a collection of vectors E. For me, it's going to be a finite set of vectors in a vector space. And then for that collection, I'm going to see what are the bases of the vector space V that I can form using the vectors in my subset. And so I think in this example, it'll be clear what I'm saying. So this is supposed to be a picture of R3. The points B, C, D, and E are on the floor. So the vectors B, C, D, and E are on the floor, the XY plane. The vector A points out. And so the question is, since we're in R3, what are the triples of vectors that are a basis of R3 in this collection? And if you do this, you see, well, if you want to make a basis, you better choose A if you want to span the whole set. You better not choose D and E because they're multiples of each other. And out of the other ones, you can choose any pair. And so basically, these are the possible bases that you can form: ABC, ABD, ABE, ACD, ACE. So this collection of bases is going to form the matroid of my collection E. Okay, and matroid theory starts from this observation that bases have this exchange property, that if you ever have two bases A and B, one in each hand, let's say, and if you pick out an element from the first basis that is not in the second basis, then you can replace it with an element of the second basis that's not in the first basis, and the result is going to be a basis. This is called the basis exchange property. This is something that it's kind of a fun linear algebra exercise, and it's really at the heart of matroid theory. And so matroids are basically going to abstract this by saying that a matroid is going to consist of a set E and a collection of subsets that satisfy this exchange property. Okay, so any collection of subsets that satisfy this basis exchange property is going to get the name of a matroid. Now, there are many matroids in nature which are going to lead to many applications. And matroid theory started from two big examples, one in linear algebra and one in graph theory. So, as I already mentioned, in linear algebra, if you start with a set of vectors inside a vector space, and if you look at the basis of your vector space that you can form with your collection of vectors, then that's going to form the basis of a matroid. But there's an interesting observation, which is that graph theory also has a notion that satisfies the same properties. If you have a graph, which I have drawn over here as an example, and if you look at the collection of edges of the graph, A, B, C, D, and E in this case, and if you look at the collection of spanning trees, so what's a spanning tree? A spanning tree is a set of edges that connects the whole graph without forming any cycles. Okay, so if you want to form a spanning tree in this collection, let's just figure out what the spanning trees are. So if you want to be able to connect this far vertex, you need to use edge A. So A needs to be in every basis. Now D and E cannot be together in any basis because they would form a cycle. So you can only choose at most one of them. And that's the only other restriction. Out of B, C, D, and E, you can choose any pair as long as you don't choose D and E. And so you find that for this graph, the set of spanning trees is this same collection B. Okay, and so we would say that the matroid of this collection of vectors, which comes from linear algebra, is the same as the matroid of this graph that comes from graph theory. And it's a fun little exercise in graph theory to show that the collection of spanning trees also satisfies this basis exchange property. Okay. So Nakazawa and Whitney observed that linear algebra and graph theory have this property in common. And so that's why they decided to define matroids. But with time, it's been surprising how many different settings also have other collections that satisfy these properties. And so there's many unintended examples of matroids that have occurred later on. A first and very important one comes from field theory, when you have the notion of algebraic independence. Again, it's a fun exercise in field theory to show that transcendence bases, which are the analog for algebraic independence, also satisfy this exchange property. There is similarly a setting in matching theory, when you're trying to figure out how to assign a certain number of people to a certain number of jobs. In that setting, you also get a matroid. There's also routing theory, which is when you have a network and you're trying to route a certain number of sources to a certain number of sinks, and you want to draw paths from the sources to the sinks that do not intersect. That also leads to a matroid. And there's many, many, many other settings where we get matroids. And so this theory that started to cover these two examples actually has many other examples. And one very important thing is that those unintended examples are an extremely important part of the theory. They really turn out to be a fundamental part of the theory. If we only did 1 and 2, we would basically be talking about linear algebra. But when we invite all these other unintended examples into the theory, then we get a much richer theory. Okay. Now, a first natural question, which was born at the very beginning, is okay. So, if we have a set of vectors, we get a matroid. Could it be that every matroid comes from a set of vectors? So we say that a matroid is linear if there is a set of vectors that gives rise to it. And so the natural question would then be, is every matroid linear? This was asked very early on, and it was answered very early on. So in the original paper, Whitney already discussed how there are examples of matrices that are not linear. And they had to be kind of artificially constructed in a not artificially, but in a very careful way. It takes some time to construct examples of non-linear matroids. With time, there's actually a very recent theorem of Nelson from 2018 that says that basically 100% of matroids are non-linear. So what this means is that if you fix the number of elements and you look at the proportion of matroids that are non-linear, then that proportion goes to 1 as the number of elements increases. But the interesting thing that happens here is that even though basically any matroid is non-linear, it's also true that almost any matroid that we think of is linear. And that speaks to our imagination as human beings. So this is a lot like, when you look at numbers, if you ask somebody to say a number, they're probably going to say an integer or a rational number. And yet we know that 100% of numbers are not integers, they're not rational. So it's a similar thing where like the things that we think of tend to be linear, but in fact almost nothing is linear. Okay. At first, matroid theorists found this very frustrating, and they wanted to fix it by adding an axiom that really characterized linearity. So they wanted to say a matroid satisfies the exchange property and some other property that really guaranteed linearity. And people tried for a very long time. But there is now a clear understanding that this is simply not possible. There's not a possible missing axiom for linearity. And this is a statement in logic that basically says that it's not possible to axiomatize linearity in a precise sense. This is a recent paper of Mayhew and co-authors, which is actually called Yes. I encourage you to search for it. It's a beautiful paper. Now, with time, though, we have learned that this is really not a flaw of matrix theory. People wanted to fix this, but we've learned that this is not something to fix. In fact, nonlinear matrices are really fundamental, and we should really embrace them if we want the full geometry of the theory. And that's what I hope to convince you of today. Okay. So my main point today is that all matrices are natural geometric objects, not just the ones that come from configurations of vectors, but all of them. And I would like to quote Giancarlo Rota, who I learned matroid theory from, and he really didn't like the name matroids, and he wanted to call them combinatorial geometries, which he thought sounded, he just thought there was a better name. So he said this quote: "When I wrote my book on matroids, I changed the name and I called them combinatorial geometries, but that didn't take. They said, that's really matroids, isn't it?" And I like this quote because I think that early on maybe it was not so clear how geometric matroids are, but I think with time I've really come to appreciate that Rhoda was really onto something important by emphasizing the word geometry in the title. And so that's why my talk is called The Geometry of Geometries. What I mean by that is that it's the geometry of combinatorial geometries, or the geometry of matroids, which really have a very geometric essence. And to explain that, I plan to share 4 geometric models of matroids that I like. This is not a complete sample. These are 4 models that I like, that I think are very rich and really teach us a lot about matroids and a lot about combinatorics. You can see them in the top if you want to follow along where I am in my talk. The models are matroid polytopes, matroid fans, conormal fans, and augmented matroid fans. And each one of those have 4 subsections where I will define them. I will talk about, for each one of these defined geometric models, what was the geometric motivation behind it? How does this construction help us understand matroids? And how does it apply in various settings? So that's my plan for the rest of the talk. So the first example is the matroid polytope. So this is a polytope which I construct in the following way. I take my collection of bases, and then I turn each one of these bases into a 0, 1 vector. So for example, A, B, C becomes 1, 1, 1, 0, 0, because A, B, and C are in the bases, and D and E are not. For example, this point right here is 1, 0, 1, 1, 0, meaning A, C, D. So for each one of the bases, I form a 0, 1 vector, and then I get a cloud of points in R to the E. E is the number of elements of the matroid. And I take the convex hull of those points. Okay, and that's going to be the matroid polytope. So it's a polytope whose vertices are 0, 1 vectors corresponding to the bases. This definition was given originally by Edmonds and later by Gilfan, Goreski, McPherson, and Serganova. Let me talk about why they thought of this. And the motivations were actually very different from each other. But this notion of matroid polytopes appears in 2 very different places in nature. So the first place that it occurs is in optimization, where the idea is that if you have a matroid, and if you have some cost function on your elements, like this, C is going to be a cost function, then you want to find the basis of the matroid that cost the least. And the cost of a basis is the sum of the cost of the elements. Okay? So for a cost function, you want to find all the bases of minimal cost. And in combinatorial optimization, it's a very natural thing to do for a problem like this, to say, okay, let's make a polytope out of these things, where there's going to be a vertex for one of these possible elements that I'm trying to optimize, and then to find the basis of minimal cost, I'm just trying to figure out, like, my minimal cost is now going to be a point, a direction in a vector space, and I need to find the farthest point of the polytope according to that direction. So that's how Edmonds found the definition of matroid polytopes. Gilfan, Goreski, McPherson, and Serganova came from a very different place. They were trying to understand the Grassmannian and a certain torus action. So let me say briefly what this is about. So the Grassmannian Kn is the collection of, given an n-dimensional space, the collection of all k-dimensional subspaces. So you form a space where each point of that space corresponds to one of the k-planes in n space. Okay. It turns out that this is a projective variety that you can actually coordinatize in a very nice way with something called a Plucker embedding. And the torus C star to the n acts on the Grassmannian in the following way. For each k space in n space, you're going to think, okay, the torus C star to the n acts by scaling each of the coordinates, and that induces an action on the set of planes. Okay, so that gives you an action of the torus C star to the n on the Grassmannian. So you have the Grassmannian, which is some variety like this, and now if you take a point in the Grassmannian and you let the torus act on it, then the torus is going to move it around to give you some kind of a sub-object, which is actually going to give you a toric variety. And toric geometry tells you that a toric variety that is embedded with coordinates gives rise to a polytope through the moment map. And when they've tried to figure out what that polytope was, they found that it's exactly this Matroid polytope. Okay, so there's a way in which the k-dimensional space that you started with has a Matroid associated to it. And when you look at that torus orbit, and you look at the polytope associated to it, you get exactly that Matroid polytope. So the Matroid polytope arises very, very naturally in that way in toric geometry. Now, Gelfand, Goreski, McPherson, and Serganova proved this Lie-theoretic characterization of matroids, which actually Edmonds to some extent also understood, which is the following. So if you start with a matroid and you form this matroid polytope, then you get a polytope like this, and then when you look at the edge directions of this matroid polytope, they turn out to all be translates of vectors ei minus ej for some values I and j. So for example, when I go from here to here, I'm exchanging coordinates 2 and 3, so this is direction e2 minus e3. Okay, and in a matroid polytope, every edge direction is always ei minus ej, and they actually prove that this completely characterizes matroids. In other words, if you take a bunch of 0, 1 points and you form the polytope, and you find that that polytope only has edges of the form ei minus ej, then it must be that you started with a matroid. So this completely characterizes matroids. So I find this a really remarkable theorem, and it says actually that we can give a new definition of matroids. I can say that a matroid is a 0, 1 polytope with edge directions ei minus ej. This completely characterizes matroids. Okay. And one thing that I find very remarkable about this is that if you want this theorem to be true, you need to consider all matroids. Now this is interesting because Gelfand, Goreski, McPherson, and Serganova started with a k-plane in n space which has a matroid that is linear. So actually the matroids that arise geometrically are only the linear matroids. They're not all the matroids. So not all matroids arise through this toric geometry construction. But when they try to figure out how to characterize these polytopes with these edge directions, they find that they actually need to allow all the other matroids in, the ones that didn't come from linear settings as well. So from this geometric viewpoint, all matroids are equally natural, whether they are linear or not, and matroids are really the setting that provide the correct level of generality. Okay. This has many applications, and let me share a few of them. So one consequence of what I was talking about torus orbits is that if you take the degree of this torus orbit in the Grassmannian, you get the degree of a toric variety, which in toric geometry, it's well known that that is equal to the volume of the matroid polytope. And using the fact that matroid polytopes belong to the family of generalized permutahedra, in work with Carolina Benedetti and Jeff Docker, we were able to give a combinatorial formula for that volume, and therefore for degrees of torus orbits in the Grassmannian. Something else that Rota pointed out very early on in work with Saj, Nicole, Joni, is that matroids form a half algebra in a very natural way. So in a half algebra, you need to have a rule for multiplying and a rule for co-multiplying. And what they noticed is that many combinatorial objects have half algebras where the multiplication is given by combining two combinatorial objects, and the co-multiplication is given by taking a matroid and splitting it into two. And if you try to do this for matroids, the most natural thing that you can do is say, okay, the way that I join two matroids is by taking their direct sum, so let me call that the product, and the way that I take a matroid and break it up into two is through deletion contraction. And so what I'm going to do is just sum over all the possible ways of deleting and contracting. They did this, they found that it was the most natural half algebra structure on matroids. Now, there is an interesting thing about half algebras, which is that every half algebra has an antipode. Antipodes play an analogous role to how in a group you always have an inverse operation that gives you for each group element its inverse. In half algebras, the analogous thing is the antipode that takes an element and gives you something that plays like the role of the inverse. For many half algebras, this is actually an involution, but that's not always the case. But one thing that is very interesting is that even though in many combinatorial half algebras it's possible to prove that there is an antipode, the formula for the antipode is actually not known, which is kind of an embarrassing state of affairs if you think that if you had a group and you didn't know how to compute inverses, you really wouldn't understand the group. And so similarly, if you want a half algebra, if you have a half algebra, you really want to compute the antipode. And in work with Marcelo Aguiar, we finally were able to find the formula. And what we found is that the insight that was missing is to think geometrically. And it turns out that the antipode of a matroid is given by its polytope. So here I have some pictures of matroid polytopes. The antipode of a matroid is given by the matroid polytope minus its facets plus its ridges and so on. So it's basically the sum over all the faces of the matroid polytope, which themselves are matroids, and with alternating signs, they give you the antipode. Okay, so that is the formula from the antipode, and it really shows you then that this polytope is actually a very algebraic thing. It shows you that if you want to understand the antipode, you have to think about the polyhedral structure of the matroid. Okay. Now, one thing that is also very pretty about this formula is that if you think about taking a polytope and then throwing out its facets, and then adding in its ridges, and then throwing out the faces of the next codimension and so on, that alternating sum actually ends up giving you just the interior of the polytope. And so you would like to be able to say that's just the interior of the polytope. And to do that, you have to basically quotient out by these kind of inclusion-exclusion relations that allow you to make a statement like this. And we were able to do this in a recent paper with my student Mario Sanchez. And I'll say a little bit more about that, but then we can really think that the antipode of a matroid is just the interior of its matroid polytope, which is what's known as the Euler map in the McMullen algebra of polytopes. So again, that polyhedral structure is very helpful here. A third point is that these vectors ei minus ej that I mentioned, I said that this was a Lie theoretic characterization because this set of vectors is one of the most important collections of vectors in mathematics. It is the root system for the Lie algebra SLN. And so that very naturally leads to the question, okay, well, what about polytopes that you can make whose edges are the root system of some other Lie algebra? And so this leads to a theory of Coxeter matroids led by Gelfand and Serganova. And then you can also think about, just like matroids are part of the family of generalized permutahedra, Coxeter matroids are part of the family of generalized Coxeter permutahedra, and that turns out to be a very pretty story of a very elegant family of polytopes. We worked this out in a paper with Federico Castillo, Chris Ure, and Alex Podnikov. The last point that I would like to make about matroid polytopes is that Laforgue, in his work on Serger and Grassmannians, introduced the concept of matroid subdivisions. So here I'm showing you three matroid polytopes in this picture on the top right. But you can also see how you can take these three matroid polytopes and and put them together to form a bigger matroid polytope. This is what's known as a matroid subdivision. And Laforgue showed a remarkable statement that if you have a matroid polytope that cannot be subdivided in this way, then that matroid has finitely many ways of being represented linearly. This is remarkable because it's actually notoriously difficult to control the linear representations of a matroid. But somehow, if you are able to understand that your matroid polytope cannot be subdivided into smaller matroid polytopes, then you can control the representations as sets of vectors. So this led to the theory of matroid valuations, and these are the functions on matroids, such that, for example, the function on the big matroid would be the function on this piece plus the function on this piece minus the overlap. And matroid valuations are a very valuable tool to study matroid subdivisions. And many authors have thought about this, and I'll mention David Spire did some very foundational work on this, which we followed up on with my students Alex Fink and Felipe Rincon, and eventually Dirksen and Fink were able to characterize all matroid valuations. And then in a very elegant paper, Chris Ure, Mario Sanchez, and Mario Supina managed to extend this to the setting of Coxeter matrix. So as you can see, these polytopes are very geometric. They give you a geometric way of thinking about matrices, and they really have these several different consequences in different parts of mathematics. So that's the first model of matrix polytopes. Let me talk about a second model, which is a matroid fan, sometimes called the Bergman fan. So for that, we're going to consider the flats of a matroid, which I will describe in the realizable case. You have your configuration of vectors, and now you're going to see what are the subspaces that you can span. So the lines are A, B, C, and D, E. So you put those here. The planes are plane AB, plane AC, plane ADE, and plane BCDE. You put that here. And then you have the origin down here and the full space up here. Those are the flats of a matroid. And we're going to make a fan, a polyhedral fan, in the following way. This is called the matroid fan. What we're going to do is that we're going to put a ray of the fan for each one of these things. So this is the origin, and these are all the rays of the matroid fan. So for example, I have a ray from 0 to AB, which is 1, 1, 0, 0, 0, because AB is one of the flats here. So that tells me what these different rays are. And then I have to say when I make a triangle. So for example, here the ray B and the ray AB are joined by a triangle, are filled in by a cone, and that's because B is less than AB in the poset. The flat B is contained in the flat AB. But for example, the flat A is not contained inside the flat BCDE, and so there is not a cone containing A and BCDE. Okay, so I describe the rays, I describe the faces. You get a face for each flag of flats that are given by a successive containment of flats. And the result of that is called the matroid fan. Okay, I call this a definition theorem because this was defined in a different way by Bernd Sturmfels. In work with Cardiac-Klivans, we managed to give this very combinatorial description. So it's a completely polyhedral combinatorial description. But let me talk about where this comes from. So the origin for this is tropical geometry. And in tropical geometry, the idea is that you take an algebraic variety, V, and you tropicalize it to a polyhedral complex that basically looks at V, looks at the behavior at infinity, and keeps track of that. So the tropicalization roughly captures how your variety behaves at infinity. And here's a definition, but I think if you haven't thought about this, maybe the good way of thinking about it is that you look at the behavior at infinity, and it turns out that this is completely controlled by a polyhedral complex. So in other words, the pieces are flat. They're polyhedral that are glued together. So these are 4 examples of tropical varieties. Okay. And so it turns out that tropicalizing varieties is not a very easy thing to do. And even for linear spaces, it's not such an easy thing to do. And so what Bernd Sturmfels did is that he suggested that tropicalizing linear spaces should be important because, of course, they're very basic examples of varieties. And he noticed that matroids would have something to do in the description. And so what we did with Cardi-Clivens is to prove the theorem that when you take a linear space as your variety and you tropicalize it, the tropicalization of the linear space is exactly the Bergman fan of the matroid of your linear space. Okay. And using some beautiful work of Anders Bjorner in topological combinatorics, we get that that this matroid fan or Bergman fan, it's a cone over a wedge of spheres. So for example here, this is a cone over a wedge of 2 circles, which you can see right there, and the number of spheres can be predicted. Okay. Now it turns out that we actually can really rethink matroids when we think in this tropical way. So I mentioned that you can take classical varieties and tropicalize them, but if you want a really robust theory of tropical varieties, you need to broaden the definition of tropical varieties, and you arrive at the definition of a tropical fan. And this is a polyhedral fan which has weights on each of the maximal dimensional cones, and those weights are such that around each cone of codimension 2 there is 0 tension. So you kind of have it's kind of in the sense of physics that around each thing of codimension 2 the things of codimension 1 pull with a total tension of 0. So you define tropical fans abstractly in this way, and tropical fans have a notion of tropical degree. And this is just like in classical geometry. If you have some variety, like a parabola, and if you want to know its degree, then you intersect it with a generic line, and you find that the parabola hits the line at 2 points, so the parabola has degree 2. Similarly, for a tropical variety, if you want to know its degree, then you intersect it with a generic linear space, but now a tropical linear space. So that comes from a matroid, and that defines a tropical degree. And you have this very nice fact that if you have a variety and you tropicalize it, then the degree of the original variety is equal to the tropical degree of its tropicalization. And Alex Fink proved this very beautiful result in his thesis, that a tropical fan has degree 1 if and only if it is a matroid fan. So in some sense, this is not a complete surprise, because if you start with a linear space has degree 1. So when you tropicalize it, it should still have degree 1. But that statement is only true for tropicalizations. It's not true for abstract tropical fans. And what Alex Fink found is that any matroid fan, even the ones that are not realizable, also have degree 1. But what I think is even more remarkable is that the converse is true. In other words, if you look at all the tropical fans that have degree 1, they turn out to be precisely the matroid fans. Okay? And so what that means is that I can rethink of matroids, and I can just make this definition that a matroid is a tropical fan of degree 1. I can just think of it in that way. It's a completely tropical definition of a matroid. And again, what I find remarkable about this is that we arrive at these matroid fans from the geometry of realizable matroids. But it turns out that to make the theory complete, you really need to embrace all matroids. From this tropical viewpoint, all matroids are equally natural, and again, matroids give you the exact level of generality that you want. This has some really beautiful applications. Perhaps the most remarkable one is the observation that started with a paper of Ha, then Ha and Katz, and then Adiprasito, Ha and Katz. As you may be aware, this is one of the papers in the citation for June Ha's Fields Medal this year. And it's the following. So this Bergman fan or matroid fan has a Chow ring. And remarkably, it turns out that this Chow ring satisfies the Kähler package. So this is point-carrier duality, hard-Lefschetz, and the Hodge-Riemann relations. In some sense, it doesn't have the right to have this property. This is a property that holds for cohomology rings, so smooth projective varieties. And this combinatorially defined ring has these properties, but that's extremely surprising, and it's not easy to prove. And this is the key technical ingredient in proving Roda's 1970 conjecture that on the law concavity of the F vector of the broken circuit of a matroid. Another important application is that of defining tropical manifolds. When we think of manifolds, a manifold is something that locally looks flat. It looks like a linear space. And so a tropical manifold should be some tropical variety that locally looks flat. But flat or linear in the tropical world means being a matroid fan. And so it turns out now that if you want to define tropical manifolds, you need to basically think of tropical varieties that locally look like matroids. So here is an example that I borrowed from Johannes Rau, where around each of these points you have a matroid, and then these matroids are glued together in this beautiful way. So that's a tropical manifold. Lucia Lopez de Medrano, Felipe Rincon, and Chris Shaw wrote a very beautiful paper studying Chern-Schwarz-McPherson classes of matroids. This is following the classical theory of Chern-Schwarz-McPherson classes, which are like Chern classes for singular varieties. And they found that this matroid fan can be used to extend that definition to any matroid. And then going from there locally to globally, you can then define CSM classes for tropical manifolds. So these are some of the applications of matroid fans. Okay. Let me now talk about the third model, which is that of Cor-normal fans, which starts with a beautiful observation that if you have a matroid and you consider its bases, then the complements of the bases also form a matroid. So for example, if ABE is a basis of the primal matroid, CD is a basis of the dual matroid. Okay? This is not a trivial statement. It's fun to prove. And this is a generalization of two facts. One from graph theory, which is the construction of dual graphs. So every planar graph, here I have one in black, gives rise to a dual graph shown in blue. So that's one construction. And in linear algebra, it generalizes the construction of orthogonal complements. So if you have a subspace of a vector space with an inner product, then you can get the orthogonal complement. And it turns out that the matroid of the dual graph is the dual matroid, and the matroid of the orthogonal complement is the dual matroid. Okay, so this simultaneously realizes these two things. And so with Graham, Denham, and Junha, we define the Cor-normal fan to essentially be the product of the Bergman fan of a matroid and of its dual matroid. We need to take a certain subtle subdivision of that. But in some sense, it's the product of these two matroids. So you're kind of understanding how the matroid and its dual play together. The motivation comes from Lagrangian geometry, and there's several ways of telling this story that I listed here. Perhaps one fairly direct one is coming from a construction of Varchenko of the variety of critical points of subspace V of a vector space. What you do is that you take the closure of the product of the projectivization of your vector space and of its orthogonal complement in the product of two vector spaces. But you do this in this interesting way that has a natural meaning geometrically, where you send x comma y to x and xy. And this twist makes this much richer and beautiful and intricate. And it's a lot of the difficulty of this theory and a lot of the fun of this theory. So we constructed the Cor-normal fan in order to tropicalize this. So again, if V is linear, then we can form this variety of critical points and tropicalize it, and we get this Cor-normal fan. And then we extend combinatorially to all matrices. Okay. I wish that we had a Lagrangian characterization of matroids, but we don't have one yet. It could be that this is related to the theory of tropical Lagrangian submanifolds, but we don't really know what to say here, and we hope that perhaps one of you will be inspired to talk to us and we could figure this out together. But this construction also has several applications. So the first one is that it turns out that the chowering of this conormal fan also satisfies this scalar package. This takes a significant extra work. We had to develop the combinatorial Hodge theory of matroids, and in general just combinatorial tools in Hodge theory to prove this. But that's the main technical ingredient in our proof of a conjecture of Berlowski in 1982, that the H vector of a matroid is also log concave. One Lagrangian consequence that we obtain is an analogous result to a result of Sava in classical Lagrangian geometry. So in classical Lagrangian geometry, when you have a variety and you have its CSM class, it's kind of a complicated construction, but when you go to the cotangent bundle of the variety and you look at the characteristic cycle in that cotangent bundle, it turns out that these CSM classes are the shadows of the characteristic cycles. And here we have the same thing, where we have our matroid fan, and now the conormal fan plays the role of the cotangent bundle here, and the CSM classes, which have a beautiful but quite intricate construction, are just the shadows of the characteristic cycles here. And that's again an important result in our proof of this conjecture. We get a rich Lagrangian combinatorics of matroids as well, and we get two beautiful polytopes, the harmonic polytope and the bipermutahedron, the first one due in joint work with Laura Escobar. Let me conclude by talking briefly about the augmented matroid fan, which is a fan that has a combinatorial definition that I'm writing here. But perhaps more than the details, I'll tell you where it comes from. Analogously to the matroid fan, it is true that this augmented matroid fan is also a wedge of spheres. Where does this come from? It comes from this construction of what has now been called Schubert varieties of matroids. This is a construction that we did with Adam Booker in 2016, where we take a subspace V of C to the n. Now we take each copy of C and we embed C inside P1 by adding the point at infinity. That gives us an embedding of C to the n into P1 to the n. And we look at the closure. And this thing has a lot of properties in common with Schubert varieties. And the augmented Bergman fan is a tropical analog of these things. And maybe I'll just briefly mention that this construction of intersection cohomology of matroids of Braden, Ha, Mathern, Proudfoot, and Wang is born from studying this variety, which has a very beautiful combinatorial structure that we uncovered with Adam Booker. And then through studying that structure further and studying the resolution of singularities of the variety, you're able to define intersection cohomology for any matroid. I wish we had an augmented characterization of matroids. We don't have one yet. But again, we have some nice applications. And maybe the main application that I want to mention here is that this intersection cohomology of matroids also satisfies the Kähler package, and proving it requires even more work. This is the technical heart of the work of Braden, Ha, Mathern, Proudfoot, and Wang, which again is one of the projects in the citation for June Ha's field medal. And there's some nice combinatorial consequences that I think I don't have the time to talk about in detail. Let me close with two remarks that I find very visionary. The first one is from that Gelfand, Goreski, McPherson, and Serganova paper in '87. And they write, "We believe that combinatorial methods will play an increasing role in the future of geometry and topology." So this is combinatorics at the service of geometry and topology. And conversely, Bose made a statement quoted by Kelly and Rota in 73 that says, "We combinatorialists have much to gain from the study of algebraic geometry, if not by its direct applications to our field, at least by the analogies between the two subjects." And these remarks really feel very prophetic today, and they have never been more true. And in my view, the awarding of June Hall's Fields Medal is very much a celebration of this vision. With that, I would like to thank you for your attention. Muchísimas gracias. And I will be happy to take any questions.
Thank you, Federico, for that wonderful lecture. Unfortunately, this platform doesn't enable us to take any questions. So thank you once again for the lecture, and goodbye to everyone.